Hello all, today we are going to discuss more advanced technique used for age detection. First one is the Mars Hildren age detector. One of the earliest successful attempts in incorporating the more sophisticated analysis into the age finding process is attributed to Mars and Hildren. Age detection method in use at the time were based on using small operators as we discussed in the previous section. Mars and Hildren argue first one that the intensity changes are not dependent of image scale and so their detection require the use of the operators of the different sizes, and the second one is that a sudden intensity change will give rise to peak or through in the first derivative or equivalently to a zero crossing in the second derivative. This idea suggests that an operator used for age detection should have the two silent features. First and the foremost is it should be a differential operator capable of computing a digital approximation of the first or second derivative at every point in the image. And second one is it should be capable of being tuned to act at any desired scale so that large operators can be used to detect blurry edges and small operators to detect sharply focused fine details. Mars and Hildren argue that the most satisfactory operator fulfilling this condition is the filter del square G, where del square is the Laplacian operator dabba square by dabba x square plus dabba square by dabba y square, and G is the 2D Gaussian function. G of x comma y is equal to e raised to minus x square plus y square upon 2 sigma square with the standard deviation sigma. Sometimes sigma is called as a space constant. To find an expression for del square G, we perform the following differentiations, that is del square G x comma y is equal to del square G x comma y upon dabba x square plus dabba square G of x comma y upon dabba y square. We are putting the value of G of x y, that is dabba by dabba x is equal to minus x upon sigma square e raised to minus x square plus y square upon 2 sigma square plus dabba by dabba y minus y upon sigma square e raised to minus x square plus y square upon 2 sigma square. We are taking the common e raised to minus x square plus y square upon 2 sigma square. In bracket we get x square upon sigma raised to 4 minus 1 upon sigma square plus y square upon sigma raised to 4 minus 1 upon sigma square. We are taking the common e raised to minus x square plus y square upon 2 sigma square. Therefore we get, collecting these terms gives the final expression that del square G x comma y is equal to x square plus y square minus 2 sigma square upon sigma raised to 4 e raised to minus x square plus y square upon 2 sigma square. This expression is called as the Laplacian of a Gaussian LOG. Figure A through figure C shows a 3D plot image and cross section of the negative of the log, that is the Laplacian of a Gaussian function x square plus y square is equal to 2 sigma square, which defines a circle of radius root 2 sigma center on a origin. Because of the shape illustrated in the figure A, the LOG function sometimes is called as a Mexican hat operator. Figure D shows 5 by 5 masks that approximate the shape in figure A. This approximation is not unique. Its purpose is to capture the essential shape of the log function in terms of the figure A. This means a positive central term surrounded by an adjacent negative region whose value increases as a function of distance from the origin, and a zero outer region. The coefficient must sum to 0 so that the response of the mask is 0 in areas of a constant intensity. The mask of arbitrary size can be generated by sampling the equation 10.223 and scaling the coefficient so that they sum to 0. A more effective approach for generating a log filter is to sample the equation to the desired n by n size, then convolve the resulting array with a Laplacian marks. Because convolving an image array with a mask whose coefficients sum to 0 yields a result whose elements also sum to 0. This approach automatically satisfies the requirement the sum of the log filter coefficients be 0. We discussed the issue of selecting the size of log filter later in this section. There are two fundamental ideas behind the selection of the operator del square G. The first, the Gaussian part of the operator blurs the image, thus reducing the intensity of structure, including the noise, at scale much smaller than sigma. Unlike averaging of the four discussed in above section is used in figure. Gaussian function is smooth in both the spatial and frequency domains and is thus less likely to introduce the artifacts not present in the original image. The other idea concerns del square, the second derivative part of the filter. Although the first derivative can be used for detecting abrupt changes in intensity, they are directional operator. The Laplacian can, on the other hand, has the important advantages of being isotropic, which not only correspond to characteristics of human visual system but also respond equally to changes in intensity in any mass direction, thus avoiding having to use the multiple marks to calculate the strongest response at any point in the image. The Mars and Hildren algorithm consists of the convolving the log filter with an input image f of x comma y is g of x comma y is equal to del square g of x comma y into f of x comma y, and then finding the zero crossing of g of x comma y to determine the location of the edges in f of x comma y. Because these are the linear processes in above equation can be written also as, that is, g of x comma y is equal to del square in bracket g of x comma y into f of x comma y, indicating that we can smooth the image first with the Gaussian filter and then compute the Laplacian of the result. These two equations give identical result. The Mars and Hildren edge detection algorithm may be summarized as follows. First one is the filter the input image with an n by n Gaussian low pass filter obtained by sampling the equation. Compute the Laplacian of the image result from the step 1 using from the example the 3x3 mask in figure 10.4a. Step 1 and step 2 implement by using the above equation. Find the zero crossing of the image from step 2. 2. Specify the size of Gaussian filter. Recall that about 99.7% of the volume under a 2D Gaussian surface lies between plus minus 3 sigma, about the mean. Thus, as a rule of thumb, the size of an n by n log discrete filter should be such that n is the smallest odd integer greater than or equal to 6 sigma. Choosing a filter mark smaller than this will tend to truncate the log function, with the degree of truncating being inversely proportional to the size of the mask. Using a larger mask would make little difference in the result. One approach for finding the zero crossing at any pixel P of the filter image g of x comma y is based on using the 3x3 neighborhood center at P. A zero crossing at P implies that the sign of at least two of its opposite neighboring pixels must differ. There are 4 cases to test left comma right, up comma down, and the two diagonals. If the values of g of x comma y are being compared against the threshold, then not only must the sign of opposing neighbors be different, but the absolute value of their numerical difference must also exceed the threshold before we can call P a zero crossing pixel. We illustrate this approach in above example. In below example, zero crossing are the key features of the Mars and Hildren edge detection method. The approach discussed in the previous section is the attractive because of its simplicity of implementation and because it generally gives good result. It is if the accuracy of zero crossing location found using this method is inadequate in a particular application, then a technique proposed by Hindrance and Medioni for finding the zero crossing with sub-pixel accuracy can be employed. Let us consider the one example for illustration of Mars and Hildren edge detection method. Consider the figure A shows the original building image used earlier, and figure B is the result of step 1 and 2 of Mars Hildren algorithm using sigma is equal to 4 and n is equal to 25. The figure sheet shows that the zero crossing obtained using the 3 by 3 neighborhood approach discussed above with a threshold of 0. Note that all the edges from the closed loop, this so-called spaghetti effect, is a serious drawback of this method. When the threshold value of the 0 is used, we avoid closed loop edges by using a positive threshold. Figure D shows the result of using a threshold approximately equal to 4% of a maximum value of the log image. Note that the majority of the principal edges were readily detected and irrelevant features such as the edges due to the brick and the tiled roof were filtered out. As we show in the next section, this type of performance is virtually impossible to obtain using the gradient-based edge detection techniques discussed in the previous section. Another important consequences of using a zero crossing for edge detection is that the resulting the edges are 1 pixel thick. These properties simplify subsequent stages of processing such as edge linking. Mars and Hildren noted that it is possible to approximate the log filter by the difference of a Gaussian, that is, the Laplacian of LOG function is given by del square g of x comma y is equal to x square plus y square minus 2 sigma square upon sigma raised to 4 e raised to minus x square plus y square upon 2 sigma square. We can see this equation before. Can we approximate by a difference of a Gaussian dog, that is difference of Gaussian, that is dg x comma y is equal to 1 upon 2 pi sigma 1 square e raised to minus x square plus y square upon 2 sigma 1 square minus 1 upon 2 pi sigma 2 square e raised to minus x square plus y square upon 2 sigma 2 square. Show that the log and dog have the same zero crossing if the value of sigma for the log is selected based on the following equation, that is sigma square is equal to sigma 1 square into sigma 2 square upon sigma 1 square minus sigma 2 square in log n sigma 1 square upon sigma 2 square. Although the zero crossing of the log and dog will be the same when this value of sigma is used, their amplitude scales will be different. We can make them compatible by scaling both the functions so that they have the same value at the origin. The profiles in figures A and B were generated with the standard deviation ratios of 1:1.75 and 1:1.6 respectively. The LOG profiles are shown as a solid line while the DOG profiles are dotted. The curves shown are intensity profiles through the center of log and dog array generated by sampling the equations we are already discussed. The amplitude of all the curves at the origin were normalized to 1. The figure B shows the ratio 1:1.6 yielded a closer approximation between the log and dog function. Both the log and dog filtering operations can be implemented with the 1D convolutions instead of using 2D convolutions directly. For an image of size m by n and a filter of size n by n, doing so reduces the number of multiplications and additions for each convolution from being proportional to n square mn for 2D convolutions to being proportional to n for 1D convolution. This implementation difference is significant. For example, if n is equal to 25, a 1D implementation will require on the order of 12 times fewer multiplication and addition operation than using 2D convolution. Then next topic is the canny edge detector. Although the algorithm is more complex, the performance of the canny edge detector is based on the 3 basic objectives. That is, first one is low error rate. That is, all edges should be found and there should be no spurious responses. That is, the edge detector must be as close as possible to the true edges. Second one is edge point should be well localized. The edge located must be as close as possible to the true edges. That is, the distance between a point marked as an edge by the detector and the center of the true edge should be minimum. The third one is single edge point response. The detector should return only one point for each true edge point. That is, number of local maxima around the true edge should be minimum. This means that the detector should not identify multiple edge pixels where only a single edge point exists. The essence of Canny's work was in expressing the preceding three criteria mathematically and then attempting to find the optimal solution of these formulation. In general, it is difficult to find a closed form solution that satisfies all the preceding objectives. However, using the numerical optimization with a 1D step edge corrupted by additive while Gaussian noise led to the conclusion that a good approximation to the optimal step edge detector is the first derivative of the Gaussian, that is d by dx e raised to minus x square upon 2 sigma square is equal to minus x upon sigma square e raised to minus x square upon 2 sigma square. Generalizing this result to 2D involving recognizing that the 1D approach still applies in the direction of the edge normal. Because the direction of the normal is unknown beforehand, this would require applying the 1D edge detector in all the possible directions. This task can be approximated by first smoothing the image with a circular 2D Gaussian function computing the gradient of the result, and then using the gradient magnitude and the direction to estimate the edge strength and the direction of every point. Let's consider f of x comma y denote the input image and g of x comma y denote the Gaussian function, that is g of x comma y is equal to e raised to minus x square plus y square upon 2 sigma square. We form a smooth image f of s x y by convolving the g and f, that is f of s x comma y is equal to g of x comma y into f of x comma y. This operation is followed by computing the gradient magnitude and the direction, that is m of x comma y is equal to under root of g x square plus g y square, and alpha x comma y is equal to tan inverse of a matrix of g of y upon g of x, with the g of x is equal to del fs upon del x and g of y is equal to del fs upon del fy. Any of the filter marks pair in our equation can be used to obtain the g of x and g of y. Keep in mind that m of x comma y and alpha x comma y are the arrays of the same size as the image from which they are computed. Because it is generated using the gradient, m of x comma y typically contains the wide ranges around the local maxima. The next step is to thin those ridges. One approach is to use the non-maxima suppression. This can be done in several ways, but the essence of the approach is to specify a number of discrete orientations of the edge normal. For example, in a 3x3 region, we can define the 4 orientations for an edge passing through the center point of the region: horizontal, vertical, plus 45 degree and minus 45 degree. The figure A shows the situation for the 2 possible orientations of the horizontal edge. Because we have to quantize all the possible edge directions into 4, we have to define the range of the direction over which we consider an edge to be horizontal. We determine the edge direction from the direction of the edge normal, which we obtain directly from the image data using the two equations. Shows if the edge normal is in the range of the direction from minus 22.5 degree to 22.5 degree, or from minus 157.5 degree to 157.5 degree, we call the edge on horizontal edge. Figure C shows the angle ranges corresponding to the 4 directions under the consideration. Let D1, D2, D3 and D4 denote the 4 basic edge direction of a 3x3 region: horizontal, minus 45 degree, vertical and plus 45 degree respectively. We can formulate the following non-maxima suppression scheme for the 3x3 region center at every point, that is x comma y and in alpha x comma y. Find the direction d of k that is closest to the alpha x comma y, and the second one if the value of m of x comma y is less than at least one of its 2 neighbors along dk, let gn x comma y is equal to 0 suppression. Otherwise, let gn x comma y is equal to m of x comma y, where gn x comma y is the non-maxima suppressed image. For example, with the reference of the figure A, letting x comma y be of p of 5 and assuming a horizontal edge through p of 5, the pixel in which we would be interested in step 2 are p2 and p8. Image gn x comma y contain only a thin edges. It is equal to m of x comma y with the non-maxima edge points suppressed. We can visualize the thresholding operation as creating the 2 additional images, that is g of n h x comma y is equal to g of n x comma y is greater than is equal to th, and g of n x comma y is equal to g of n x comma y is greater than equal to TL, where initially both g of nh x comma y and g of nl x comma y are set to 0. After thresholding, g of nh x comma y will have fewer non-zero pixels than g n or l x comma y in general, but all the non-zero pixel in g of nh x comma y will be contained in g of nl x comma y. Because the latter image is formed with the lower threshold, we eliminate from g of nl x comma y all the non-zero pixel from g of nh x comma y by letting g of nl x comma y is equal to g of nl x comma y minus g of nh x comma y. The non-zero pixel in g of nh x comma y and g of nl x comma y may be viewed as being strong and weak edge pixel respectively. After the thresholding operation, all the strong pixel in g of nh x comma y are assumed to be valid edge pixel and are so marked immediately. Depending on the value of th, the edges in g of nh x comma y typically have gaps. Longer edges are formed using the following procedures. Locate the first one is the locate the next unvisited edge pixel p in g nh x comma y. Mark as a valid edge pixel all the weak pixel in g nl x comma y that are connected to a p using say 8 connectivity. If all the non-zero pixel in g of nh x comma y have been visited, go to the step D, else return to step A. Set to 0 all the pixel in g of nl x comma y that were not marked as valid edge pixel. At the end of this procedure, the final image output by the Canny algorithm is formed by appending to g of nh x comma y all the non-zero pixel from g of nl x comma y. Summarizing, the Canny edge detection algorithm consists of the some basic steps. That is, first one is smooth the input image with the Gaussian filter. Second one is compute the gradient magnitude and angle images. Third one is apply the non-maxima suppression to the gradient magnitude image. Fourth one is use the double thresholding and connectivity analysis to detect and link the edges. These are the basic steps are used for the Canny edge detection algorithm. Let us considering the figure. The figure A shows a familiar building image. For comparison, the figure B and figure C shows respectively the result obtained earlier in figure B using the threshold gradient and figure D using the Hildren detector. Recall that the parameter used in generating those two images were selected to detect the principal edges while attempting to reduce irrelevant features such as edges due to the bricks and a tile roof. The figure D shows that the result obtained with the Canny algorithm using the parameter TL is equal to 0.04 and TH is equal to 0.10. Alpha is equal to sigma is equal to 4 and the marks of size 25 by 25, which correspond to the smallest or integer greater than 6 sigma. These parameters were chosen interactively to achieve the objective stated in the previous section we are discussing for the gradient and mass Hildren images. Comparing the Canny images with the other two images, we see significant improvement in detail of the principal edges and at the same time more rejection of the relevant features in the Canny result. Both the edges of the concrete band lining and the bricks in the upper section of the image were detected by the Canny algorithm, whereas the threshold gradient lost both of these edges and the Hildren image contained only the upper one. In terms of filtering of irrelevant details, the Canny image does not contain a single edge due to the roof tiles. This is not true in the other two images. The quality of the lines with regard to continuity, thinness and straightness is also superior in the Canny images. Results such as this image made of the Canny algorithm tool of a choice for edge detection. Next one topic is edge blinking and boundary detection. Ideally, the edge detection should yield the set of pixel line only on edges. These pixels seldom characterize edges completely because of noise, breaks in the edges due to the non-uniform illumination and other effects that introduce spurious discontinuities in intensity values. Therefore, edge detection typically is followed by linking algorithm designed to assemble the edge pixel into meaningful edges and or region boundary. In this section, we are discussed the three fundamental approaches to edge linking that representative technique used in practice. First one is local processing. One of the simplest approaches for linking the edge point is to analyze the characteristics of the pixel in the small neighborhood about every point x, y that has been declared an edge point by one of the techniques we are discussing in previous section. All the points that are similar according to the predefined criteria are linked, forming an edges of pixel that share common properties according to the specified criteria. The two principal properties used for establishing the similarity of edge pixel is the kind of analysis are first the strength, magnitude and the direction of the gradient vector. The first property is based on the equation we are already discussed. Let us consider in S, x, y, x, y denote the state of the coordinate of the neighborhood center at a point x, y in an image, and edge pixel with the coordinate s, t in S of x, y is similar in magnitude to the pixel at x, y if magnitude of m of s of st minus magnitude of m of xy is less than equal to E, where E is the positive threshold. The direction angle of the gradient vector is given by the equation, and edge pixel with the coordinate s of t in S of x, y has the angle similar to the pixel at x, y if magnitude of alpha s, t minus magnitude of alpha x, y is less than equal to A, where A is the positive angle threshold. The direction of the edge at x, y is perpendicular to the direction of the gradient vector at that point. The preceding formulation is computationally expensive because all the neighbors of every point have to be examined. The simplification, particularly well suited for real-time applications, consists of the following steps. The first one is compute the gradient magnitude and angle array m of x, y and alpha x, y of the input image f of x, y. Form a binary image G whose value at any pair of coordinate x, y is given by G of x, y 1 if m of x, y is greater than Tm and alpha x, y is equal to A plus minus Ta and 0 otherwise, where Tm is the threshold and plus minus Ta defines the band of acceptable direction about A, and A is a specified angle direction. Third step is scan the rows of G and fill set to 1 all the gaps set of zeros in each row that not exceed a specified length k. Note that by defining a gap is bounded at both the end of one or more 1s. The rows are processed individually with no memory between them. To detect the gaps in any other direction, theta, rotate G by this angle and apply the horizontal scanning procedure in step 3. Rotate the result back by minus theta. Let us considering the one example, that is a figure A shows that the image of a rear of a vehicle. The objective of this example is to illustrate the use of the preceding algorithm for finding the rectangle whose size makes them suitable candidate for license plates. The formation of this rectangle can be accomplished by detecting the strong horizontal and vertical edges. Figure B shows the gradient magnitude image m of x, y. Figure C and D shows the result of step 3 and step 4 of algorithm obtained by letting Tm equal to 30% of the maximum gradient value. A is equal to 90 degree, Ta is equal to 45 degree, and filling it all the gaps of 25 or fewer pixels. Use of a large range of allowable angle directions was required to detect the rounded corner of the license plate enclosures as well as the rear windows of the vehicle. Figure E is the result of forming the logical OR of the two preceding images, and figure F was obtained by thinning figure E with the thinning procedure we are discussed above. As figure F shows, the rectangle corresponding to the license plate was clearly detected in the image. If it would be simple matter to isolate the license plating, form all the rectangles in the image using in fact the width to the height ratio of the license plates has a distinctive 2:1 proportional. Next one is the regional processing. The location of the regions of the interest in an image are known or can be determined. This implies that knowledge is available regarding the regional membership of the pixel in the corresponding edge image. In such a situation, we can use a technique for linking the pixel on the regional basis, with the desired result being an approximation of the boundary of the region. One approach to this type of processing is functional approximation, where we fit the 2D curve to the known point. Typically, interest lies in fast executing techniques that yield an approximation to essential features of the boundaries such as extreme point and concavities. Polygonal approximations are particularly attractive because they are capture the essential shape features of the region while keeping the representation of the boundary relatively simple. In this section, we develop the illustrate an algorithm suitable for this purpose. Before starting the algorithm, we discuss the mechanism of the procedure using the simple example. Let us consider in the figure shows a set of points representing an open curve in which the end points have been labeled A and B. These 2 points are by defining the vertices of the polygon. We begin by computing the parameter of a straight line passing through A and B. Then we compute the perpendicular distance from all the points in the curve to this line and select the point that yielded the maximum distance. If this distance exceeds the specified threshold T, the corresponding point labeled C is declared a vertex. The figure A shows the line from A to C and from C to B are then established. The distance from all the points between A and C to line AC are obtained. The point corresponding to the maximum distance is declared a vertex D. If the distance exceeds D, otherwise no new vertices are declared for that segment. A similar procedure is applied to the point between C and B. The figure B shows that the result and figure C shows the next step. This iterative procedure is continued until no point satisfy the threshold test. Figure D shows the final result, which as you can see, it is a reasonable approximation to the slope of the curve fitting in the given points.